we're good. It's partially about what we had finished talking about. It's about the Lorentz group and how the Lorentz group gives rise to chirality in the context of spinors.
Spinors?
Yes.
Well, the Dirac spinor is a four-component spinor, and you can decompose it into a left-handed spinor and a right-handed spinor. And there are two representations of the group SL2C. So 2 by 2 linear matrices, every matrix is linear. 2 by 2 linear transformations, determinant 1 with complex coefficients. So they're 2 by 2 matrices. In fact, I can write them down. This guy goes as essentially e to the z dot sigma, and this one is e to the minus z star dot sigma. So these are the two different representations of SL2C. And SL2C is what we think of as the Lorentz group, which of course is really O31. The comma means that this thing, it's transformations that preserve inner products taken with this metric, which is what we
That's a
flat space-time.
an exercise in Peskin and Schroeder.
It's an exercise in Peskin and Schroeder?
Yeah, and I'm struggling with it right now. That's why I asked. I think you just did it though.
Well, I discussed this in the book.
Yeah,
in the second section on group theory. Okay, so much for that question. Let me go back to what we were talking about. And I've been actually rewriting some of the book, hoping to get a second edition going. And so let me just say a little more about the very beginning, because the very basic assumptions, because I think they can be quite confusing. And so the idea that the way I think of it is that space-time is some sort of a manifold in a higher dimensional Euclidean space. So this is space-time, and it's inside something that's I don't know, E8 or E9. Let's just call it En, some higher dimensional Euclidean space, and it is some curved space. But I'm thinking of this thing as physical, because it's really physical. But on this thing, we have for each point P, the points P are physical, but we describe the points with coordinates P of x or P of x prime, and then we can talk about small changes in the location of the point P. And dP is some ei of x dxi, and we can also write it as e prime I of x of x prime, say dx prime I. In other words, we can have two coordinate systems or any number of coordinate systems describing points on the space-time manifold, and when we change the position, that infinitesimal change has got to be the same in both coordinate systems. And so what are these vectors EI? These things are called tetrads, which just means that there are four things. In fact, I think I've got sort of a redundancy there. Tetrad means four, and then I've got an S for plural. So it's a little funny, perhaps. In German, they're called Vierbeins. But I just think tetrad sounds so much nicer than Vierbein. shorter anyway, and for somebody who doesn't touch type, it's a real advantage. Anyway, so what are these tetrads? These guys are vectors that span a tangent space. And in this picture there, in which we have space-time is just a two-dimensional surface moving in time, so it's a three-dimensional space rather than four-dimensional. The tetrads would span a two-dimensional tangent space at each point. And in general, the tetrads, no matter what the manifold is and how many dimensions, whatever, the tetrads are all, well, they're not necessarily tetrads. If we have a space-time of more than four dimensions, they would be, I think the term that some people use is Vielbein, where Viel is German for many, so many bein. I'll have to come up with a Greek equivalent. Anyway, So that's the basic idea. Now, these vectors here are vectors in this. We can think of them as four. If we're just talking about ordinary space-time, the tetrads can be thought of as vectors in of course, they are vectors in the tangent space. They span the tangent space. And there are only four of them because they are the derivatives of the point with respect to a change in the coordinates, small change in one of the coordinates. So there are exactly four of them. And if you have four vectors, then they span a four-dimensional space. They needn't be orthogonal or anything, or normalized, but they span a four-dimensional space. So they can, and now in that four-dimensional space, we can set up a Euclidean coordinate system and give them components. And moreover, they're also vectors in this higher dimensional embedding space. And now, you can take 2 points of view. I think it's useful to take both. As Yogi Berra said, when you come to the fork, take it. You know, that's because on his property, he had so much property that he had a road coming in, which then went this way to his house and then went the other way to the house. So either way you took the fork, you got to the party. Anyway, I'm completely distracted from whatever the hell I was talking about.
Second way to look at it.
Right, thank you. So you can either think of them, as most people do, which is as spanning the tangent space, but then the problem is you move to another point B, you have a different tangent space. So you have an economy that you have four-dimensional vectors spanning a four-dimensional tangent space, but you go to another point and you've got a different set of four-dimensional vectors spanning a different four-dimensional vector space. Each four-dimensional vector space you can think of as Euclidean. The other way of thinking about them is that these vectors are tangent vectors in, these tetrads are tangent vectors in different tangent spaces, but they're all n-dimensional vectors in the n-dimensional embedding space. And that way, there's just one space, you give them one set of coordinates, and then as they move around, of course, they change, their coordinates change, but at least you sort of know what you're doing. It's a little less, you have more coordinates, but it's simpler. Fewer coordinates, but it's more complicated, more dizzying, in other words. Okay, so that's that. Now, we could, of course, use a Euclidean metric, but in order to get the physics right, we're going to use the Minkowski metrics, because we've got one of these dimensions is time, which is, of course, somewhat screwy. Time is, we don't really understand time. We pretend we sort of do, because we get older. But it's not something we really understand. And so what we're going to do, of course, is we're going to say EI of x dot EJ of x we're going to use this as, we're going to say that that is a sum. We can, from one point of view, we can say, maybe I should even be more elaborate, A is 0 to 3, B is 0 to 3, EA of X, A to AB, EB, J of X. So this is the way where you have a different change in place at each point. And of course, we're going to call this Gij of X. So this is going to be our metric tensor. And alternatively, we can say this is the sum A equals 0 to n, B equals 0 to n, a different set of EA of X, and now a sort of different A to AB. Maybe I should use different letters like C and D, C, D, EDJ of X. But either way, it's still Gij of X. And the reason why we think of this as the metric tensor is that the thing that we want to be invariant is dp squared, the separation between 2 points, so point P here and point P prime there, so P prime. We want the separation to be, which is physical, we want that to be invariant. And dp squared then is Gij dxi dxj, which is to say it is dp, of course, is di dxi dotted into ej dxj. And as I said, to get the physics right, we use the Minkowski metric. Now, why do we do that? Well, what we know from special relativity is that this separation in special relativity it's called in flat space ds squared, which is basically dx squared minus dt squared. I'm setting c equal to 1 to save Charles. And so we know that in ordinary special relativity, if that this is the thing that's the important separation, and that we can that the equations of special relativity don't change if we change coordinates, as long as we keep this thing constant. And the next step that Einstein made in general relativity was he said, well, I don't know if he said well, but what he said was, in effect, that we want to keep invariant this dp squared, but dp squared was more general than this. It was just Gij, dxi, dxj. And now the point is, as we'll see in a moment, I'll sort of jump ahead and then write it down. As we'll see in a moment, it's always possible locally to change coordinates so that Gij just becomes eta ij, so that we have this. In other words, we can go to ds squared equals dx squared minus dt squared in the neighborhood of any point. But of course, elsewhere, that change of coordinates will transform g to eta. So basically, we can transform g to eta in the neighborhood of any point. And so his idea then was that if we transform, so the principal equivalence is that, first of all, you can transform any space-time metric to the metric of flat space in the vicinity of any particular point, and that, moreover, in the vicinity of that point, where you have this being the metric, in these coordinates, because space is flat, his statement was that gravity goes away, and you just have the physics of special relativity. So that's the principle of equivalence. And this is what you sort of experience if you get in an elevator and the cable breaks and down you go. You feel, oh great, there's no gravity, but you are just floating there freely, and it's so in an accelerating reference frame, the gravity goes away. Of course, if you were measuring things really carefully, you'd see that points on one side of the elevator, the other side of the elevator went, and they were both on trajectories pointing to the center of the Earth rather than straight down. Okay, that was a long shebang there. Let me let's see. If you examine this a little bit, you see that the tetrads themselves are covariant vectors. They have one covariant index. So this is a second-rank covariant tensor that transforms the usual way. I'm not going to read you all that. Now, since the tetrads transform as EIA of X prime, they are partial xj, partial x prime I, j a of x. So this is the way they transform. We can arrange to transform them such that this is delta ai, again, in the vicinity of a particular point. And what is the rule there? Well, it's very simple. It's much simpler. It's twice as simple as the other one. We just call this E inverse ij. Well, obviously, if we think of this as a matrix, then E inverse E gives you the identity. And so this thing is just the identity of that matrix, the inverse of that matrix. And then what happens is dp squared, which is d prime ij of x prime, dx prime I, dx prime j. This is then d prime I of x prime dot d prime j of x prime dx prime I dx prime j. And this is then putting in the metric of space-time. This is e prime a of x prime a to ab, and I'm just going to use ab whether we're talking for or n. E prime b j of x prime, again dx prime I dx prime j, and so this is then delta ai, a to ab, delta bj, dx prime I, dx prime j, and this is then a to ij, dx prime I, dx prime j. Okay, and so this is what we call, well, it is dx squared minus dt squared equals ds squared, and this is, by the way, minus the square of the proper term. Okay, so the idea is that we can always change to flat space in a vicinity of a point, and when we do that, all the Christoffel symbols become zero, vanish, and everything is like special relativity. And so that's basically the equivalence. We were talking, we defined G upper ij as the inverse of the metric tensor. So this is delta ik, and in particular we can raise a tetrad index like this. And so that means that ei dot ej is gij, well, let's make this okay. Gij ej dot ek, and that's gij gij g lower ik, and this is just delta ik. So these things, if you raise one space-time index using the inverse of the metric tensor, you get a tetrad that is dual to the ordinary tetrad. That is to say, these are orthogonal, and they are orthogonal with respect to the Minkowski metric. So the dual vectors are orthogonal to the ordinary tetrads. The dual tetrads are orthogonal to the ordinary tetrads, where orthogonality is defined in terms of the Minkowski metric. Okay. So let's jump on to what we were talking about last time, and I'll just review that material a little bit. And I'm also going to say something about torsion. I've changed my mind about torsion. I think I'll tell you why when we get. So let's think about a field F of X, and I'm writing it in invariant form Fi of X, Ei of X. And as I said, we take a derivative of this. So this is something I did last time. We get partial F on partial X. Well, I need to look at the notes here. Let's make that XL. Ei plus Fi partial XL of P lower I. And the point is that this thing here is no longer in general in the tangent space. And so it makes sense to take an inner product of this with one of the dual vectors. And so in fact, if we define this Levi-Chibitov connection as the following: Ek dot partial Ei partial X L, then we can say that Ek dot partial F partial XL is, well, it's going to be Ek dot, and now we're going to have, let me just write this as Fk comma L what do I call it? Ei plus Fi Ei comma L. And these guys are orthogonal, and so this is Fi comma L. No, it's Fk comma L, because we were summing over I. Fk comma L plus gamma K Li Fi. So this is this Ek dotted into Ei comma L. Okay, we're all happy with that. All right. So this is the Levi-Chibitov connection, and we can define, this defines a covariant derivative dl Fk. Maybe I should put that K over here, actually. So, and this is sometimes written as DL FK, although I think the K should be here. Anyway, this is then FK, comma L plus gamma K Li F I. And you see why I think the K should go over here. It's that the K doesn't stick to the F because it turns into an I. Okay. Now, so this is the way Einstein basically set things up, although I don't think he used these tetrads. That was an idea of Cartan's. But when Einstein was doing this, and in fact when Cartan was inventing these tetrads or moving frames, this was, 1915, 1916, 1918. Quantum mechanics wasn't seriously invented until 25 or 6. Electron spin was discovered probably the late 20s, I don't remember at the moment. And then the Stern-Gerlach experiment had to be performed before they realized it would spin 1/2 and so forth. So there was a lot of things didn't get straightened out for a while. In fact, this was an incredibly rapid change, a period of enormously rapid change in physics. It's just infinitely faster than anything that's happening now, outside of Witten's brain. So anyway, so you see, they weren't thinking about fermions, and you see, if we have a fermion, then we might write, if we wanted to write the fermion field in an invariant form, say a Dirac fermion with 4 components, we'd write this as psi A EA. And what are these? Well, I shouldn't use the same form. All right, I'll just use EA. Maybe I'll use FA. So F means F for fermion. And so these, we might think of these as 4 vectors that are associated with a particular place. And if under a Lorentz transformation, the psi goes one way, then these F go the other way so as to compensate. And then psi is invariant under Lorentz transformations. One might go further and say, well, all right, I don't know quite how to go further because I haven't really developed this. I just want to say that when you do try to do general relativity for fermions, something that most folks on general relativity skip, then the possibility of torsion coming in is much greater. And so when I said this will be a torsion-free course last time, what I meant was, as long as we stick to ordinary classical pre-Fermion, pre-Dirac general relativity, I don't want to say that torsion is necessarily out, but once one does include the fermions, then the possibility of torsion is much greater. And I haven't thought this through enough to tell you about it, so I'm just going to maintain the torsion-free stance, but I'm saying that you ought to think more about the fermions. And it's one of the unfortunate things is there's been a huge separation sociologically and psychologically and intellectually between the people doing general relativity and the people doing particle theory. And it's never good when you have these total separations. Okay. Anyway, this gamma, another way of writing this gamma is what's called the Christoffel symbol, and it would look like that. I think that's an absolute crazy way. I suppose there's a latex form for it, but it still is. It looks pretty bizarre to me. Because now we go back to the pre-Dirac way of writing things. This thing here, of course, gamma k Li being ek dot ei comma L. Well, ei is p comma L, so this is ek dotted into p comma il, but the double partial derivative is symmetric in the two indices, and so this is the same thing as gamma k il. So we went through parallel transport last time, and it was basically that the dual vectors then are orthogonal to the covariant derivative, and that's the way f changes. And I gave an example. The example, by the way, just one of you missed it last time. Well, the example is done in the book, but basically you start up here at the North Pole, and you bring the thing down this way like that, and then you keep it pointing that way, and you bring it across 90 degrees, and then you bring it back up. It starts out at the North Pole. It starts out. All right, wait a second. It starts out being -1, 0, 0. So that means it's basically the phi vector. This is phi hat. So phi hat at the North Pole, or at least one step down toward New York from the North Pole, or toward Greenwich, England from the North Pole. The phi vector is pointing that way, and so right. I'm having trouble now getting this straight. X would be going this way, Y this way, and Z up here. No, 0, 1, 0. That makes sense. 0, 1, 0. So it's pointing the Y direction. We're going down the x-axis. Then you parallel transport along here until you get it to the point where it's on the y-axis. Then, of course, it's pointing at -1, 0, 0, because it's pointing in the -x direction. And then you move it up here, parallel transporting it, and when you get up there, it's perpendicular to the original one. And that is due to the curvature. And that's a nice example of parallel transport. Of course, in four-dimensional space-time, parallel, the conditions are that this should vanish. Okay. So we've been talking, when I was talking here about covariant derivative, I was talking initially about a field expressed in terms of contravariant, where is it? Expressed in terms of its contravariant components and its covariant tetrads, the original tetrads. On the other hand, you can consider a vector field V that is written in terms of the dual tetrads and the covariant components. And then when you take the derivative, V comma L, what you get is VK, EK, comma L. And so this is VK, comma L, EK plus VK, EK, comma L. And to figure out what this is something that I went through briefly last time. You take the orthogonality relationship, between the dual vectors and the ordinary dual tetrads and the ordinary tetrads, and we differentiate them to get 0 equals ek comma L dot I plus ek dot I comma L. And so that tells us that ek comma L dot ei is equal to minus ek dot ei comma L, and that is minus gamma k I L. And so this covariant derivative of the covariant components of a vector field looks like this, and when we dot that in, what we get is vi comma L minus vk gamma k IL. So it's just, so this minus sign arises from that, and arises from differentiating this orthogonality relation. And what this means is one of the general relativity is a complicated theory, no two ways about it. But there are some remarkable cancellations, and one of them is that if you take the covariant curl, covariant derivative uses semicolon instead of a comma. So minus vi semicolon L. Well, if you write this out, it's the ordinary curl. And then the two other components are minus vk gamma k li, and then plus vk gamma k il. Well, of course, these two guys are the same, and so that cancels. And so it's just the ordinary curl, or the ordinary antisymmetric derivative. And so that's an enormous simplification, and once again, it's to get back to what Maxwell did. He had this Maxwell tensor was fl comma I minus fi comma L, and so the ordinary covariant derivative of it is the same as so in other words, this thing here is a generally covariant second-rank tensor. In other words, if we might say, well, what is this FIL? Well, we'd have to do covariant derivatives here. But because it's antisymmetric, the covariant derivatives are the ordinary derivatives. So in other words, we could say it's this, but that's the same thing as L comma I minus a I comma L. So in other words, this is a second-rank covariant tensor. And the implications of that are that the homogeneous Maxwell equations are Fi JKL, F JK comma L, well, it's just that. 0 equals this. And this is a second-rank antisymmetric tensor, and in fact, if we put a semicolon here, it wouldn't make any difference because of something else, which I guess I should mention. What would this be if we put in a semicolon? Let's put in a semicolon. We have epsilon, well, all right, let's just leave it with a comma, JKL, and let's just compute what what this would be. Let's just go to AIL semicolon K plus AKI semicolon L plus ALK semicolon I. So that's basically what is happening here if you just replace. In other words, here I'm just talking about an arbitrary rank 2 covariant tensor, and then taking its covariant derivative like this, and then taking cyclic combinations. And what happens is, this is AIL comma K minus gamma M I K AML minus gamma M LK AIM. And let me just make it, the details are in the book. You add in all the terms, and what happens is you just have AIL comma K plus AKI comma L plus LK comma I. So in other words, the sum of the cyclic combination of the three covariant derivatives of the second rank covariant tensor is the same as the sum of the ordinary derivatives. And consequently, Maxwell's homogeneous equations were absolutely correct in general relativity as well as special relativity, because first of all, they were correct because F is antisymmetric, and so this was second rank, and then the ordinary derivative works because you don't need the covariant derivative. So this is just some of the remarkable, well, it's basically that if you can do experiment, you only get the theory right, and eventually. And the point is that electrodynamics was, I mean, you have a long-range force, so you don't need microscopic measurements, and it's of moderate strength, and so you can do perturbation theory, figure everything out, and so forth. So Maxwell got almost everything right. Just a tiny change in the homogeneous equations. Okay, now, one of the things that I used here, by the way, was how to compute the covariant derivative of a second-rank tensor, and what I used was this relation here, which is to say a generalization of a generalization of this rule here. So in other words, what was done here was to take one of the indices, say I, and take that index, just sum it with the gamma, and then put down here IL. And if you have a rank 2 tensor, then you do the same thing with both indices. So you have IL here, and you have the I here, and then the L there, and then you sum over these guys, and then you have the extra index K comes out here and there. So in other words, you just repeat. So the general rule is, we've got this rule for differentiating rank 1 covariant and contravariant tensors, which are just vectors, and we just apply it in the same way to higher structures. I think we've got the null for now. And there's a consequence of this, namely that, well, one way of thinking about it is we can imagine doing this, defining a 3-index gamma, and all this is just lowering one of the indices. So in other words, we just lower the upper index here on the M and call it that. This is a symbolic relation, And remember, this thing isn't a tensor, okay, because it transforms inhomogeneously. So this is just a definition of this guy, which also isn't a tensor. But it's a useful thing. And we can go the other way. We can say that GMK on gamma KLI is gamma M. Now,
So is it too far to say that the tetrad is now covariant? Like, right?
well, yeah. This is contravariant, and the ordinary tetrad is covariant.
Right, but if you go up one more
Why don't you
equation,
turn the thing?
if you go up one more equation, no, down. Well, there's your definition. There's your definition of gamma.
Of gamma.
Right. So if I have the k,
This is contravariant. This is
right. So if I make the k, a covariant 3, no, it's not a tetra. If it's gamma KLI, then is it covariant E
well,
K?
no. All right. Let's distinguish things here.
Yeah.
Whether an index is contravariant or covariant is one thing, and that says how that index transforms under general coordinate transformations. But the point is that once we take the dot product of this with the derivative, it no longer transforms like a tensor.
Okay.
It no longer transforms linearly under general coordinate transformations.
Okay.
And presumably the real reason for that is that we're differentiating a tetrad.
Okay.
So when you differentiate the tetrad, you get something that's pointing outside the vector space. Because on the other hand, we're dotting it into this so that the thing cancels. But anyway, it's not it transforms inhomogeneously.
Okay.
And
But those
we know how this transforms. We can figure out how this transforms, and if you see how it transforms, there is an inhomogeneous piece.
those are the same that span the tangent space on some point on a manifold.
The E's span the tangent space, yes.
So that doesn't change when you dot them. The tangent space is still spanned. We didn't change anything about the tangent space, right?
Yeah, but their derivative.
Or do we have?
Well, what about their derivatives? The derivatives don't necessarily span the tangent space, because if you think about that example that I gave way earlier, I don't know where the hell it is now, but yeah, here it is. Well, let's just talk about theta hat. Okay. So theta hat is pointing in the, if we look over here, theta hat is pointing down here, it's pointing down there, over here it's pointing down. But now if we take the derivative of theta hat with respect to, what was it, I've lost it.
Is it R?
R? What's that? R. The derivative of theta hat with respect to theta, I think is minus R. But, yeah, that's right. So that if we take the derivative of theta hat with respect to theta, we get a vector that's pointing in.
Yeah, towards
And that's no longer in the tangent space, it's perpendicular to the tangent space. Okay, so I owe you guys some candy. God, yeah, use another chair, please. Here's the candy. Well, we're in fact sort of at the end of the lecture. I might as well use up that board there. Okay, let's just get this one thing done immediately, quick, and we'll probably need the whole board. So I've made these definitions here. And the next thing is to think about what this is. So gamma k Li is equal to cos GKM gamma m Li, and that's GKM EM dot EL comma I. And, well, let me just say, it's obvious that this thing, I don't think I need to write it anymore, it's obvious that this is gamma KIL, just because these guys are symmetric. And now let's consider GIL comma K. Well, this is EI comma K dot EL plus EI dot EL comma K, and I see now that I skipped something, and yeah, let's just let this thing lower this index M, so that means that this is equal to EK dot EL comma I. So that's what that actually is. And so now we can rewrite these guys, this derivative, and say this is equal to gamma lick plus gamma ilk. Okay. All right. Now, if we then permute these, what we get is gamma ki comma L is gamma pickle plus gamma kill, and G LK comma I is gamma plea plus gamma, well, I can't pronounce that. Anyway, whatever it is. And so now if we add all three together, this plus this plus this, oh no, we don't add them up. What we do is we take this one plus this one and subtract that one. Then what we get is GKI comma L plus GLK comma I minus GIL comma K. And now, if you keep track of these, what you can see is that when we subtract this one, oh shit, I think I picked the wrong one. All right, not this one. This one. Getting that somehow, did I make a mistake? Oh, these guys, here, we forgot something. These guys are all symmetric in the last two indices. So this one here does cancel this one. Lick cancels this one. And so what we get is that this is equal to, oh, and then these other two are the same because Li and IL are the same. So this is equal to 2 gamma clee. Good, it's one that I can pronounce. So what we get is that gamma clee is a half G ki comma L plus G LK comma I minus GIL comma K. And consequently, the Christoffel symbol or the affine connection, gamma SIL, which is of course GSK gamma plea, is equal to a half GSK, and then, let me just write ditto. It's these two terms. Okay. So basically that's, now this is actually quite important because this tells you that the affine connection, and this is the thing that gives you gravity, is related to the inverse of the metric tensor and derivatives of the metric tensor, ordinary derivatives. And so gravity is related, gravity is controlled by derivatives of the metric tensor, and so this gets us back to the equivalent principle. If you can transform to the arbitrary g to eta ij, you can, I've showed you can do it at one point, but if this manifold is smooth, then you can do it if you blow up space-time, in other words, you look microscopically, then you can arrange for these guys to be zero to arbitrary precision in a sufficiently small neighborhood of any given point. And that's the equivalent principle of gravity goes away there. And of course, if you're in a falling elevator, it pretty much is like that. When I was at Fudan University, I was in a building that was looked like this. And these towers were 30 stories high, and I was on floor 26. And I was the only one there in the winter because the Chinese all go home for New Year's. And so I was freezing. They turned the heat off. Unbelievably cold. But anyway, what I want to tell you is that I had real appreciation of the equivalence principles. You get in the elevator, and the thing would drop like a stone in the beginning. It was a high-speed elevator because they had 30 stories to traverse. And in fact, what would happen was it would drop like a stone, and so it was accelerating down, and then it would come to a constant high velocity going down. It didn't keep accelerating, but it would accelerate down, and then it would stop and go. It wouldn't stop, but it would go at a constant velocity. And when it went at a constant velocity, I could feel the weight under my feet, and that was transforming to back to relative to the Earth, an inertial system, and consequently one where I felt gravity, whereas I felt much less gravity as the thing was accelerating down. And I always thought that the elevator was going to stop at some flaw, but no, it just kept going. All right, that's enough. Let's turn this thing off.
I can only take elevators about
One.
three. I can only take.
How do you turn it off? You just hit power?
Red button.
Right here?
Yeah.
Okay, thank you.